Right. Okay. So I think you can start, and then we'll figure out anything as we go.
So I hope at least you can hear me.
Yes, we can hear you. Right.
Thank you for the invitation. I'm sorry I couldn't come because I'm in Paris for another conference this week. So I will try to give an overview of various problems, and I will start with the waist double Hurwitz numbers. So the weight double Hurwitz numbers, so you consider, Hurwitz numbers, you want to count the number of branch covers of P1 with some control ramifications. So here is P1, two special points 0 and infinity. And so I hear actually echo of my voice. I don't know if that's normal.
Yeah. I'm not sure how. Can maybe turn off our microphone? Yeah. Can you still hear? Yeah, now I cannot. Okay.
No, I don't hear anymore.
Okay, so just yeah, I think go ahead. We are going to mute ourselves, so you shouldn't hear any echo. Just let us know.
Yeah. So we are considering branch covers of P1, and in particular over 2 points. So this can there can be various sheets, and there's some ramification above. So this should be above 0. And above infinity, it does something else. For example, this. So this is a branch cover of degree 4. So in general, you want something of degree D. And here above 0, you see that there's some ramification. So you can encode that into the length, the length of rows of a partition. So here the partition will be this one. And on the other side, I will have this partition. And you may also have, so let me add another thing. You may also have ramifications somewhere else. So you may have some other ramification points here. And when you consider double Hurwitz numbers, you want to control the ramification above 0 and infinity. So we call that lambda and mu. And for the other ramification points, you will rather put some random ramification profile. And random here in a bit generalized sense, because you're just going to weights, and the weights may not be positive. And this is encoded into an element B, which I want to see as a linear combination of cycle types. And that is an element of the center of the symmetric group algebra of sigma D. So it's a combination of C lambda, that's the class corresponding to the sum of all permutations that are in a given conjugacy class, whose length of cycles are given by the size of the rows of lambda. And there may be some coefficients. And if you want to count the number of branch covers with that type of ramification data, so this is something that goes back to Hurwitz, you can actually, so I'm going to call this number of such branch cover H lambda mu B, you can express it in terms of representation theory of the symmetric group. In particular, what you're going to do here, so up to a normalization, you're going to multiply C lambda B and C mu and take the coefficient of the identity in this product. And this is living in the center of the symmetric group algebra. And this is because when you look at P1 minus the branch points, and so the branch cover of two isomorphisms determined by the which representation of pi1 you have, and the pi1 is as a presentation as the product of the cycles which goes around this point is equal to the identity. So there's various types of Hurwitz number you can consider. So that's what the weight part is about this B. So there's something called simple, if you only allow simple branch points for these extra points. That would correspond to take B, which is 1 over k factorial if you have k of them. And then, so the permutations correspond to how is the local monodromy. So how the sheets are permuted. If you have simple branch points, you should have transpositions. And so the contribution of all these points here, these red points, is going to be a product of transpositions. And since you don't want to label this point, you divide by 1 over k factorial. But you can consider many other types of waves, and that's something that John studied a lot. In particular, there's something I will call B strictly, and then some gamma, which is the sum over k. So k would be again the number of these points. Gamma is a parameter to make a generating series. And here I want to take the elementary, or let's say for the moment, I still want to take a product of transpositions. However, so that would correspond to a strictly monotone situation, which is this funny condition that, okay, so when you have a transposition, it's AI, BI, and you can always assume that AI is smaller than BI, and strictly monotone will mean that you want that the BI is strictly increasing. And you can also consider the weakly monotone. So here it's max, whatever, so this BI, I call it max of tau I, and it should be strictly increasing. And here I want the same with a weakly increasing sequence of transpositions. So there are three particular examples. There are many others which are interesting, but this one will play an important role in my talk.
Gaetan?
Yes.
The gamma is just a parameter, and that's powers, right?
Gamma is just a parameter. Okay. So there's a second aspect to this. And this is something, in fact, I learned from directly from a discussion with John when I visited Montreal, I think around 2015, when I was working on this with Mathieu Guépaquet, is that there are three descriptions of this. So you want to consider this space, which is the center of the symmetric group. And as a vector space, I mean, this has three descriptions. It's also the space of the ring of symmetric functions. So the isomorphism is the vector space. So symmetric function is countably many variables. And it's also the fermionic Fock space. So the semi-infinite wedge. And each of these three descriptions, you can learn a lot on the others, because, for example, over here, this is a ring, while here, it's not obviously so. It's not the same structure. You have certain group actions here that you can transport to the other side. And this Fock space is also something which is at the heart of 2D Toda hierarchy, an integrable hierarchy. So here, if I take the power sums attached to a certain Young diagram lambda, and one normalized by a symmetry factor, the isomorphism just extending this to the conjugacy class. Okay. Then there's a particular action one want to consider is the regular action here. I mean, after all, this is a group algebra, a commutative one, because it's in the center. So you have the regular action on itself. And it's interesting to look at the Jussies-Murphy's elements. So J, which is the sum of all transposition with maximum index J. And these are not in the center. However, if you take any, so let me give a name lambda to this ring of symmetric function. If you take any symmetric polynomial, you can evaluate it on the Jussies-Murphy, and then at some point you put zeros. And that happens to actually generate the center. So you can take such an element and then multiply, act on this on C lambda, or transport this action to act on the ring of symmetric function. So one interesting property of this, so I'm going to call that Rj, not writing the zeros. When you act, so not on the power sum, but on the Schur basis, which on this side correspond to the idempotence. In fact, the Schur functions are eigenvectors for this action. And here you see the polynomial R applied to the content of lambda, which is the set of all. So you have a Young diagram, there's a row and a column position, and the set of all I minus J, or a box in lambda. And that's eigenvalue. On the other hand, if you come back from how these Jussies-Murphy's elements are defined and put into some polynomial, you would see that this is acting, if I call that BR, I could take that as my intermediate ramification profile. And you can try to see how is that acting on the conjugacy class, on the power sums. And so I'm probably don't count on me for all the factors to be right in this talk. It's probably some symmetry factors which are off. But here you would see that you get the sum of exactly these double Hurwitz numbers with intermediate ramification profile BR. And then it's going to be a P mu divided by automorphism of mu. So in particular, if you want to have these simple branch points, you would take P1, so as P1 of J to the K over K factorial. If you want B, so the strictly monotone Hurwitz numbers. So before we had these elementary symmetry, well, we had this. If you look at what it means in terms of the J's, it corresponds to the elementary symmetrics. And so this should be this product. And on the other hand, if you want the weakly monotone, you will get the HKs, which are those ones. Sorry, I think I mixed them. This here.
Probably vice versa.
Yes, this one is like that. While you get the H if you do this. So some of the inverse, these two operators up to a chain flip on the sign of gamma, they're inverse to each other. Good. And so what I learned from John is that, so there's a 2D toda tau function, which is something which live in lambda, so a completion of the double tensor product. And there's a trivial tau function, which is the sum of S lambda tensor S lambda. So you can imagine it's expressed in terms of symmetric polynomials in two sets of countably many variables. And then you can act on this by Rj on the first factor, identity on the second factor. And you still get, so what John calls a hypergeometric tau function. And because S lambdas are eigenvectors, it has a very simple form. It's still diagonal. However, the interesting point is that the combinatorics of Drusis-Murphy tell you that actually it's also a generating series of Hurwitz numbers. When you express this in terms of power sums. Good. So now, another questions. I will move to discussing the relation with the topological recursion.
Gaetan, may I ask a short question?
Yes.
Yes, hi. Actually, something that I was afraid to ask for a long time. This Hurwitz tau functions, are they related to what is called descendant form when we have ramification profiles at fixed number of points?
I think you can express certain descendant form generating series with certain operators B. Correspond to a particular choice of B, if I remember.
Particular choice, but not any choice.
Not any choice.
Mm-hmm. Okay.
So
It's a generalization, excuse me, it's a generalization of descent d'enfant. But descent d'enfant is a particular case.
Yeah. Okay. So if you, for a long time, people only considered simple Hurwitz numbers, which means so it doesn't have to do with the intermediate points, it's just that you fix the trivial ramification over infinity. And there was a conjecture coming from string theory, the Bouchard-Marvenio conjecture, which exploits the relation between, Hurwitz numbers can be realized at a certain limit of topological strings. And the Bouchard-Marvenio conjecture stated that if you apply topological recursion TR on this curve, then you actually get the simple Hurwitz numbers. You can extract the simple Hurwitz numbers, so with this trivial ramification here. And by now, so this was around 2008, and by now this has three different proofs. So it's a well understood thing, but that was the starting point. So it's conjecture and then its first proof. And then there were various generalizations of this, where people started to realize that if you put another type of way, so another B, then you still get topological recursion. So more and more families, that was 10 years ago, of simple but waste Hurwitz numbers were shown first conjecture and then shown to satisfy topological recursion. And the spectral curve, so I should maybe say it's a recursion on what? Here, from this stage, you're not totally satisfied with counting just branch covers, you want to fix their topology. So you want to fix the genus and fix the length. So what's the number of premises of 0 in the branch cover? And you're doing connected branch cover, so you have a certain genus G. And it's a recursion on 2G minus 2 plus N. And the spectral curve, so Y is a function of X. In each of these problems, so that's the easy part, because you just need to find the case G equals 0, N equal 1, and very often you can compute that by elementary means. So in most of these problems, you could actually compute what the spectral curve should be. And then the question was, can you prove topological recursion? And a lot of people worked on this and managed to prove that in several cases. Each time the method was a bit more technical, so it was a case-by-case thing. Then there was a work by a series of work by Alexandrov, so by John, with Alexandrov, Chapuis, and Hénard. Who I think were the first to tackle this problem, but for to try with double Hurwitz numbers. And here there's a nice idea, because now you have two sets of parameters. So what do you recurse on? They desymmetrize the treatment of the 2 points. So more precisely, what they're going to do, so you want to define some omega GNs, which you want to compute. And this is going to be, so there's a sum over all the ramification when you have exactly n premises above 0. So here you're going to put x lambda 1, x n lambda n. And here the lambdas are not ordered. And here you want to put your, let's call that B, a lambda and mu. And so what do you do with the mu? So these you represent as variables. But for the mu's, you just put some parameters. So it's Q mu1, Q mu L mu over automorphism of mu. And this one you treat as parameters, not as variables. And you probably want to do something like this. Okay. And what they managed to prove is that at least when B is of the form Rj with an R polynomial, and there was a few more assumptions, but that's the essential one, then indeed you get topological recursion for these things. And so you get a spectral curve depending on the Qs. Good. So it was the first case where you actually families of Weiss-Hurwitz numbers that were satisfying topological recursion. And this assumption was technically important from them. The proof was not working without it for good reasons. And so it fell short of proving it TR for, let's say, simple branch points. I mean, arbitrarily many simple branch points, which would correspond to take R, which is exponential of some gamma P1. Because then the R of J would actually be the sum over K, gamma to the K, and then product of K transpositions arbitrary with a K factorial. So it cannot do this case, which was a bit of a pity. But then there were other approach on this problem, which was some building also on this work. In general, for this Hurwitz problem, so it was maybe the merging of ideas coming from this work and ideas that were existing before, which was really exploiting the Fock space description of Hurwitz numbers. So it's another approach which was developed by the group of Shadwin in Amsterdam. So there's Julian Bakowski, Shadwin, and many others, Levansky, etc. And so they really use Fock-Speck expressions. Which is secretly, which is exploiting so this fact that, okay, so we started with something in this description of the Fock space, and we bring it to the fermionic Fock space. And here there's a nice operator you can express in terms of Clifford algebra acting on that. And you use these sort of operator or expressions to get two things. So the general strategy was you can always get Curtin-John equations. This is not hard with these operator formalisms. And the hard part is you can try to prove that these generating series, which are just formal series in the x's, actually have an analytic continuation on the spectral curve of the problem. And that, for a long time, was pretty hard. So that's why people tackle case by case, each time being more ingenious with the algebra. And together, these two things imply the so-called loop equations, which are equations which are directly solved by TR. So at this point, we tried, so this was a work with, so Do, Levansky, sorry, Karev, and Elena Moskovsky. So we tried to adapt those techniques to tackle this case. And this was much more technical, but we succeeded. And so it gives, so it is for that case, you get TR. It's around the year. I think it was finished during the early COVID times. You get TR for that spectral curve. So you write it, you get it in parameterized form. So here are the Qs, which encode how it behaves at the branch curve behave at infinity. You truncate it somewhere, but you can put this truncation arbitrarily large. And here you have the same polynomial. And shortly after, in fact, Bishkov, Kazarian, Dunin-Barkovsky, and Shadwin in fact, managed to completely systematize that analysis. So they made it systematic. By using operator manipulation in the Fock space. So it's a beautiful word because automatically they could derive TR for the largest class possible. Of weight Hurwitz, double Hurwitz numbers. And some of this closes a bit this problem opened almost 15 years ago. And not only close the problem, but it allows to tackle other problems. And now I want to come to this. So this is an operator method. So this brings me to a third topic, which is matrix models and free probabilities. And here I want to recall a bit the history, I mean, of these recent developments. In the year 2001, so one knows that two matrix models, so two Hermitian matrix models, with a measure of this form, you have two potential for the matrices, and then they're coupled with trace of M1, M2. They can be solved by orthogonal polynomials. And as much as orthogonal polynomials, it's well known, they satisfy a second order differential equation. By orthogonal polynomials also satisfy differential equations. And you can also change the coefficient of the potential. So you're in fact compatible ODEs. But now you have two types of polynomials. So you get two lax pair descriptions for the two polynomials. And in 2001, Marco, Bertrand, and John made the observation that the spectral curve of these lax pairs, so I call it L1, were dual, I mean, were essentially the same. Also, the lax pairs have different size. They're quite different, L1 and L2 as operators, but the spectral curve is the same. And shortly after, building on works on matrix models that were happening in the early 90s, Chekhov, Hénard, and Orentin, in fact, systematized solving the large n expansion of these matrix models once you assume it exists. And that gave rise to the theory of topological recursion. The theory was invented to solve matrix models for large n expansions. And it was working for the one Hermitian matrix model, but also for the two Hermitian matrix model. And this topological recursion, so it's a recursion again on G and N for these quantities, which are the coefficient of so the large n asymptotic expansion of the cumulants of the resolvent of the matrices. So in the one matrix model, it would be this. So it's for those objects here. And once you know those correlators, you can get back to the free energy by a sort of integration. But in the two matrix model, you have two matrices and STR for the correlators of each of the matrix. So in Vapor, you have two ways of getting the free energy. This led NR to propose. So there was two ways, and so NR envisioned that actually so you should of course give rise to the same free energies, getting it from the two spectral curve, and the two spectral curves are related by this sort of kind of exchange of the role of X and Y. So that exchange of X and Y should give the same free energies in general in topological recursion. And you call that the symplectic invariance. So also the correlators are very different if you exchange X and Y, because you can think in the two matrix models, correlators of one matrix and correlators of another matrix. The free energies, which are the sum of the omega G0, are the same. So formulating this precisely and even trying to prove it is quite tricky. And there was some argument of NR and Laurentin based on the analysis of the two matrix model, which was pretty involved. And yes, is there a question?
No.
So I was looking for a simpler way to understand this duality. In particular, we know that matrix models, matrix integrals are generating series for maps, so for ribbon graphs. And I was trying to understand what does that mean in terms of maps. So I looked for a combinatorial interpretation of the symplectic invariance. Or at least, if not the symplectic invariance, so that's still not realized, of the X and Y exchange. And in fact, there is something which is known where this X and Y exchange appears in a bit of a disguised form, which is in free probability. So in free probability, which is something which was introduced by Voiculescu. So there's a Voiculescu R transform. And it tells that if you have a sequence MK, which you would call the moments, you can construct from it what would call so the free cumulants. Kappa K. And I will not exactly write the way Voiculescu wrote it. I will write it in a way which is convenient for us. So you make this generating series. The relation actually becomes nicer in this way. So with M0 equal 1, and here again, kappa 0 is going to be equal to 1. So you make this generating series, and then you make these other generating series. So here it's in terms of 1 over X, and here it's in terms of W. And so there's a certain definition, I mean, from Voiculescu, and essentially this definition amounts to say that X of WX is equal to little x. So if you call Y equal W of X, then you realize that X is Bx of Y is a functional inverse. So that's an example of XY exchange. And in the context of a matrix model, so here let me say, so maybe what these moments correspond to, if you have on the space Hn of Hermitian matrices of size n, You take a probability measure, which is UN invariant by UN conjugation. For example, something expressed in terms of traces. You can look, so MK, you can try to look at the large N limit of the trace of MK. M is my matrix. And assuming that this sort of limit exists, that will define your moments. And then the free cumulants also have an expression. I'm going to come to that. And in terms of maps, this is counting. So if you have a model which is here, which is a perturbation of the GUE, it is going to have so when P is a formal perturbation of the Gaussian measure, this MK first exists and then is counting disks, so maps with the topology of a disk. Of perimeter K. And we found, I consider the following problem. So maps, it's you have various faces that you glue together, and there's a so it's a graph on the surface. There's a boundary. Here's a topology of a disk, and this has length K. But in the way these things are defined, I mean, the Feynman graphs for these matrix models, they actually, these maps can be pretty singular. So you can have some bubbles and bubblings here. Okay. So you could say, well, I try to express these geometric zero maps in terms of simpler maps. So we call fully simple maps. And we found that kappa K counts fully simple maps. Which are those without touching. So this core, for example, is simple. And it's expressed by, in terms of geometric series, by this relation. Okay. So the other thing we know is that topological recursion computes, because it applies to matrix models, it also applies to enumeration of maps. So it computes the omega gen, which are counting maps of genus G with n boundaries. And to be precise, so topological recursion, so the spectral curve is this W of X, geometric series of ordinary, so this one we call ordinary disks. So that disk counting. And then you also need an input, which is omega 02, which you slightly shift to form an object called the Bergman kernel. And so these, as analytic continuation on a certain curve, which is the spectral curve, you take the function x, the variable x, then you express y in terms of x, and you apply b, and you apply tr, and you obtain the omega g1s. That's the result of essentially of inner. So we're thinking, okay, now if I exchange x and y, I know that for this, I'm counting something else. I'm counting fully simple maps. Could it be that when I apply TR to the spectral curve with exchange x and y, and then the same B, because that's how symplectic invariants work, the same Bergman kernel. So that was the conjecture which we formulated precisely with in the thesis of Elba Garcia Failde. That should compute what I call omega gn check, which is, or xgn check, which is counting fully simple maps of any topology. And the first thing is, what about the B? So the B should be related to omega 0,2. And combinatorially, yes, this actually is true. So the fully simple cylinders, essentially the picture is like this. So you have two boundaries where they can touch each other. There's boundary 1, there's boundary 2, and they touch each other on these lines. And the maps is in the middle. So you can have this kind of touching, and then you can have bubblings a bit everywhere here. Everywhere. And when you express combinatorial leads, that give you combinatorial leads that give you a relation between W02 and X02. Remove this check, which is exactly telling you that it's the same B. So when you do this shift and you express in terms of W variable in terms of X, you get the same. So it was a good evidence that yes, at the spectral curve level, the realization of the X and Y exchange is exactly going from maps to fully simple maps. And then the conjecture was does that extend to all topology? And this conjecture was resolved, so proved. And in fact, in two ways, one with Séverin Charbonnier and Elba Garcia Failde, and about the same time by the group of Chadrin. Okay, so I guess I close to how much time do I have? Is it 3 minutes or? I don't hear anything. If you type in the chat, I can see, even if I don't hear. Okay, so make big signs if I go over time and you want me to stop. So I just want to close a bit the circle. I want to return to Hurwitz. Because in fact, maybe I can write things like this: fully simple maps with some boundary length, which I encode in a partition lambda. Roughly speaking, you have a universal relation independently of which probability measure I take, which kind of K of faces I look at. So there is a universal relation. Okay, it's 5 minutes. So it's for any P. So fully simple maps can be obtained from ordinary maps. With a certain kernel here, which is exactly the weakly monotone Hurwitz numbers, is just a certain width. Gamma is -1/n. And here you need to put the normalizing factor. And you can also invert that, write it in the other way, ordinary maps. So it's here disconnected maps, any topology. You count everything. Right here, mu. There's some symmetry factors in this relation, which I'm not writing here. And here it's in terms of the strictly monotone Hurwitz numbers. So that's multiplication. Okay. And there's at least 3 ways to see that. One is by Weingarten calculus, so that I didn't really explain why that would be true, but another way which may be more familiar to part of the audience, it comes from the character expansion of the HCIZ integral, which relates it to the monotone Hurwitz numbers. That's from the work of Gulden, Gepake.
I think it should be here. Okay. Fine.
And Novak.
Gaetan,
Yes.
the HCIZ integral is for weakly monotone. What
Yes.
is there also a matrix integral for the strongly monotone?
So it means that you can go in one direction, but since this the operators in the Fock space that create these weakly monotone or strictly monotone are inverse to each other up to a change of sign in the parameter. So once you know one of these relations, you automatically know the other. These two matrices are somewhat inverse from each other.
But is there a matrix model representation of the tau function?
Or of this one, you mean? That I don't know.
Simple.
Make it-
Fully monotone.
Mhm. And there's also a bijective proof. Good. So no, I need to conclude it in 1 minute, but what I want to say is that, so these are fully universal. And in fact, you can study these kind of relations. So Z is a collection, is a function on Young tableau, arbitrary function. And you can study relations of this form. So for example, let's take this one. We sum Z mu check. Okay. So that's an expression of this relation, but here you start with a z lambda here, and you can define or you start from z mu check, and you define some z lambda from this relation for any lambda. And that you can express in the Fock space. So you can actually encode, you can define a vector in the Fock space by, these are the coefficients in terms of Schur functions. And then the corresponding vector of the check is going to be a certain operator on the Fock space, which is exactly the one generating those weakly or strictly monotone Hurwitz numbers. So in the way I wrote it, Z is obtained by the certain operator generating the strictly monotone applied to the Z check. And then you can use operator methods to deduce, with a lot of heavy computations, that's using the method of Chadwin et al., to deduce actual functional relations between WGNs, which you define from Z in the same way that you would define, you would go from disconnected to connected by taking a log, and then you extract a certain genus thing, so a certain coefficient of a parameter n, and the WGN check, which you define in the same way, but from Z check. And if you specialize this relation to G equals 0, you in fact going to retrieve the relation between higher order free cumulants and usual cumulants. And this type of function, so at the functional relations, and this problem, and you also obtain it in higher genus as well. So that was not defined in free probability, but that also works. And this thing was defined at the combinatorial level in a work by Collins, Mingo, Schniadi, and Speicher, but they couldn't prove more from their definition than these relations for the R transform and the second order, which is here expressed in the fact that the same B. And some of this method, which is this detour via Hurwitz numbers and the Fock space, allowed actually to solve this problem, which was open for a while. And there's even more recently some more better development. I mean, you can express generally what X and Y exchange is doing for an arbitrary spectral curve using the operator method. That's a recent paper of Chadwin et al. And so now we're much closer to actually prove or understand well this symplectic invariance property. And it's really this interaction between different domains was extremely fruitful and inspiring. Thank you very much.
Okay. I hope, can you hear us now?
Yes.
Okay. Are there questions from the audience here or the audience in Zoom? There's a question now. Oh, all the way to the back. Just a second.
Yes. Can you hear me?
Yes.
Yes, thank you very much for that. I have two questions. The first one is horrible. I apologize for it. So what is exactly topological recursion?
Yes.
You want to ask also the second one, and then I see in which
Yes,
order?
the second one, yes, you want to skip the first one.
No, I'm going to try to answer in a more
The
compact.
second one is, since there are Euclid-Murphy elements for other group algebras, is there something like Hurwitz numbers, not for type A, not for symmetric group?
So there is in particular recently the type B, so which was I think initially studied by, so I'm not exactly sure, I think Natanzon and then Orloff were maybe the first to study that, but please correct me if wrong. So in this type B, you replay the symmetric group by the Sergeyev group. And that corresponds, in fact, it's interesting because it counts Hurwitz numbers with a spin. So you have a spin structure on the cover, and you count the branch cover with a sign depending on the parity of the spin structure. And so that you can do. The very start of my talk for the B, so it's well known, I think, from this work of that is from Orloff, but maybe also some other people. And then the operator part and the treatment of this operator thing and how to get to topological recursion, that's also was done by Alessandro Giacchetto, Danilo Levansky, Rainier Kramer. They conjectured the topological recursion for this. And shortly after, with the same technique, so this very flexible technique, Alexandrov and Shadrin, in fact, proved the conjecture. So the answer, at least for type B, yes. Most of this, I mean, most of the theory extends, and it has very interesting applications in algebraic geometry. Now I should try to answer your first question. So in topological recursion, you start with a spectral curve. I don't want to make it long. I just want to say roughly what it does and what it looks like. And so a spectral curve is just, if you want, a complex curve, but you realize it as a branch cover, let's say of P1. And you equip it with another function, let's say a meromorphic function. And there's a little piece of data, an extra one, which maybe I don't want to discuss too much, but you can let me call it omega 02. And out of these data, so there's this black box called topological recursion. Which tell you consider omega 01, which is y dx, that you want to see as a function of x. But secretly, it's more a meromorphic one form on the spectral curve. And omega 02 is part of the initial data. It depends on 2 points in the spectral curve. And then there's a formula that computes omega gn by recursion on 2g minus 2 plus n from these initial cases there's a residue formula. By computing residues. So it's of this shape. You look at the sum of residues at zeros of dx, which are the ramification of this branch cover here, which has nothing to do with the branch cover I was counting. Here, this is a fixed curve with a fixed function x. And then there's some kernel that depends on the initial data. And here there's something which depend on the rest of the variables, which only involves omega g prime n prime for 2g prime minus 2 plus n prime smaller than 2g minus 2 plus n, so that this is a recursion. So I can add one sentence, but first I would like to ask, what is your background?
Well, I'm algebraist, not algebraic.
Oh,
Okay.
sorry. She says that she's an algebraist and not an algebraic geometrist.
Okay, good. So you may have heard of the Virasoro algebra.
Yes.
Good. And so how this definition is made is to produce, so these things all together, they give rise to a kind of a highest weight vector for Virasoro, several copies of the Virasoro algebra at a central charge, the cell dual central charge. So it's, if you want, there's some operators which are going to kill a generating series, which I call Z, which is a bit like the tau function actually. It encodes, so the tau encodes the information about all the omega GNs. And there's some operator that kill that. And it's only half of the operator that kill it. So topological recursion is a solution of those Virasoro constraints, which has in this context, a very specific form, which is universal and only depends on the spectral curve. And the reason why we're interested in that is because these omega GN, if you fix a certain spectral curve, like the one coming from Hurwitz counting problem, so the counting of disks, or if you take the spectral curve of an integrable system given by a lax pair, or if you take the spectral curve of a matrix model encoding the way the eigenvalues behave with a large N limit, the omega GN in this case is going to compute, essentially to solve your problem completely by this induction. The only thing that changes in the initial is the input, which is the spectral curve. So in 5 minutes, that's what I can say.
Can you send my thanks to the speakers?
Thanks to this. She's thanking you, but the microphone is a bit far, so I am relaying information. Any other question or comment? John?
Unless there's somebody else, I don't want to always take precedence. So Gaetan, very nice talk. Thank you. Did I understand correctly that you said that if you know the weekly monotonic double Hurwitz numbers, then you can somehow also calculate from that the weekly monotonic ones?
I say something a bit different. You consider this double Hurwitz number as an infinite matrix whose rows and columns are indexed by partitions. And I'm saying that if you know this relation, you can deduce the other. Just because these matrix, so it's the matrix.
We don't see what you're writing. So where is it?
Here.
Yeah, it's okay.
There's relation 1 and relation 2.
Oh, okay.
And one of them implies the other just by the fact that these two matrices are inverse of each other. And this is clear on the Fock space formalism because here, when you express the Drusis-Murphys, it's just either you put that or that. So up to changing the sign of gamma, when you multiply by the two together, you get the identity.
So can you scroll up again to the 1 and 2? So was that an inequality or an equality?
That's an equality.
So you can read off these fully simple maps and also the ordinary maps from a knowledge of the weighted Hurwitz numbers.
I'm saying there's yes, if you know, that's maybe the best way to express it is this kind of way. So you have a vector. If you know one vector, this operator defined in terms of Hurwitz numbers gets you to the other side, and that's invertible. And if you invert it, you actually get the transition matrix given by the weekly monotone.
And D is just an infinite linear map.
D is this in the Fock space, it's exactly these two things here.
Oh,
Except I put gamma, okay, gamma is maybe 1/n in my case.
it's the weight generating function with Jusis-Murphy elements put in.
Yes.
Oh, okay. That's pretty explicit. Okay, thank you.
Okay, so other questions? Online, maybe? If not, we can thank the speaker again.
Thank you very much.
And now we have a break